magnetic field on the current carrying current carrying wire. Right? These are the two cases, right? So in the first case, we're going to see how how the magnetic field created when you have a current flowing through a wire, right? So this is the first case that we have to discuss, right? So okay, so imagine I have a wire. Okay. hmm No, imagine I have a wire. Okay, this is my wire. Okay, and there's a current flowing through it. Let's say this and this. Okay. Mhm. And it is like placed on some plane, which is like this.
So when we do a P5,
Yes. But maybe after the end of the syllabus, or maybe like up to a certain point, then we stop the syllabus and then we begin with P5. Maybe these are the two possible options. Okay. So let's imagine that this is the wire I have. Okay. And there's a current flowing through the wire. Okay. Maybe it's going upward or downward. These are the two possibilities, right? Let's imagine that the current is moving upward. Okay. In the first case, and in the second case, let's say the current is moving downward. Okay. And obviously there should be some sort of circuitry that is connected in order for the current to flow, right? So um, after that, when we observe this experiment in reality, so due to the current moving in the wire, there will be magnetic field generated around like a circle, like in circles, right? And which you can work out using the Maxwell right hand grip rule. Okay, so this is the rule that you can use, right? To find out the direction of the magnetic field. Okay, now in this rule, we generally remember this as a grip rule, right hand grip rule. Okay, where you have your thumb. Okay, that is pointing in the direction of current, and current means the flow of positive charges. Okay, current is a positive charges, right? Right. So and you have to curl your finger, okay, and the curled finger basically tells you the direction of the magnetic field, right? In every cases the curled finger will going to tell you the direction of the magnetic field, right? So in this case, in the first case, if you have the current moving upward, right, and you just curl your finger around around the wire, so it will show you the anti-clockwise direction of the magnetic field, right? Are you guys getting the same thing? If you guys please give it a try.
yes,
Yes, okay. And what about the next one?
yeah.
So basically, it looked like the magnetic field looks like this. Mm, okay. Yep, that's perfect. Just a second, please. So the third one would be like this. Okay. So these are the three magnetic field lines that we have, right? And if you work out for the direction, so the direction will turn out to be the clockwise, right? So clockwise means it will be moving in this direction. Wait, clockwise? No, anti-clockwise, like this one. Okay, so okay, clear. Mhm. So this is going to be the first case where you have the magnetic field like this, right? Now, in the second case, the magnetic field is basically clockwise. Okay, so the clockwise you have to draw the similar thing, but just make it clockwise. Mm. Come on. Okay, let's just first. Okay, and then second, and then actually they'll give you 3 mark for that. So that's why you have to be a little bit precise. Um, the second one and the third one. Mhm. Yep. Okay, that's good. So if you have the current flowing into the page or current flowing out of the page, these are the two cases. And um, okay, and in the second case, the direction is going to be the clockwise, which mean in this direction, in this direction, and in this direction, right? If you if you view the whole thing, so by the way, they'll give you 3 marks for these three things. Let me just write that down. The first mark will be awarded for the correct direction of magnetic field. Okay. Okay. The second mark would be awarded for um, at least three circles. Okay. And the third is going to be the separation of the circles should be should be increasing, right? So these are the three things that you have to keep in mind, okay, when talking about or when drawing this, okay. Now, is that clear? Okay, these are the three marks that they'll give you, okay. Uh, and if you just look at the diagram, so this is like the increasing, right? This separation is increasing, right? So this is what you have to show, right? And the correct direction, right? So these are the three things that you have to show right now. By the way, the current coming out of the plane is represented as a dot, right? And the current going into the plane represented as a cross, right? So if I make a dot here with a, okay, so current is coming out of it, okay, and over here, current is going into the plane, right? So you have to make it a cross, right? Like this. So please always keep in mind these are something that you have to mention while drawing. Basically, this portion is all about the drawing. Okay, so this is the first thing. Okay, now the second thing that is okay. If you place the two wires together, then what will happen? Then let's see. I have the two wires. Okay, and the two wires are having the current flowing in the same direction. Okay. Let me pick this one. Okay, copy and paste. Right. Okay, I have two wires, right? Two setups. Placing right next to each other. Okay. Okay, like this. Okay. So in this case, you can see that the both the wires having the current causing the magnetic field to be created around the wire. Okay, but the magnetic field for this for the left wire is in this direction, and the magnetic field for the right wire is in this direction, right? Which means the magnetic field are in the opposite direction, right? So, and you know that whenever you have the opposites, so they'll attract each other, right? So for this one, the two wires will attract each other, right? So we're saying, or we'll say, uh, the magnetic field is, yeah, the magnetic fields are in the opposite direction for both the wires, for both the wires, okay, which causes them to attract, which causes them to attract. each other, right? Now, um, if they are not placed like in a cart, so they will look like this, right? They start looking like this. They'll start bending towards each other, right? By the way, please keep in mind the magnetic field is like very low that you can't even observe that in your real life, right? Like if you have a charger and the wire, like the connecting cable, so if you plug the charger on and there will be the current in the wire, so there won't be any magnetic field around the wire, right? Even if there is a current in it, right? Because the current is very small, right? And that causes the magnetic field to be very smaller, right? And then the insulation material of the wire also reduces the magnetic effect of the wire, okay, and it reduces it like the material in the insulation reduces the magnetic field of the wire to a very lower value, right? So you can you can easily observe that, right? So this is the first case where you have two wires connected together, right? And like placed together, and they both have the same current direction, right? And the magnetic field are in the opposite direction, right? Now, I have one question. Whether like let's say in the first wire is in the first wire, let's say the current is I1, and in the second wire the current is I2, right? Can you guys tell me, okay, the currents are different by the way. So can you guys tell me whether the magnetic force will be different or same for both the wires? What do you guys think? Yes.
What's it?
Whether the magnetic force will be different or same. If you have the current in both the wires, right? So obviously both the wires will start attracting toward each other, right? So this wire will be attracted toward the other wire in this direction, right? Due to the magnetic field, okay, and this wire will be attracted toward the other wire in this direction, okay. Okay, these are the two possibilities, right? These are the two forces basically. Force, um, force by two on one, okay, and force F by 1 on 2, right? This is wire 1, let's say, wire 1 and wire 2. Okay, is that clear? Yes. I am asking if we have a current in the wire, okay, so due to the current, okay, whether it is same or different in value, right? Due to that current, will the forces on each wire be equal to and opposite to each other, or it will be different? Yes. Any idea, any relation?
No, sir.
No relation.
Can you explain?
Okay. Okay, so basically, um, irrespective of the value of the current, if they both wire have a flow of a current, right? Then in both of the wire, they both experiences the magnetic force of equal magnitude and opposite in direction due to the Newton's third law, right? So over here, if you talk about the force, wait, force on each wire. Okay, so force on each wire, force will be equal and opposite uh, on each wire. Each wire, okay, due to Newton's third law. the Newton's third law. Okay. And the Newton's third law required the two different objects, right? Same type of force, okay? Equal in magnitude, opposite in direction for the same amount of time, right? So every condition of the Newton's third law is basically fulfilled, right? So that's why we have the same equal and opposite forces on both the wires, right? Irrespective of current, by the way, okay? Um, Irrespective of the value of current, right? This is like um, frequently asked question in 1 or 2 mark for these type of question, right? So this is one case, right? Now the other case is if I have the two wires, okay, but the current are moving in the opposite direction. Let's say I have one, wait, one over here, one for this, okay, and the other is this one, okay, paste, okay. Now, so for this one, mm, can I make it fit into each other? Fine. I can just enlarge this one. Okay. For this second case, the both the wire will going to experience again the forces. Okay. Um. Yep. So, equal in magnitude, opposite in direction, right? And but if you look at the magnetic field pattern, so magnetic field for this wire is going in this direction, and it is going in this direction, right? So this actually represents that the magnetic field, like if I draw proper lines, so the magnetic field would be like this. Wait, let me just. Okay, fine. Now, so the magnetic field would be like this. Like this. Okay, and like this. Okay, okay. So basically, they're moving out from this direction. Okay, mm, like this. Okay, and they're coming in from this direction, right? Like this, right? So if you can see, so if you can see that the magnetic field pattern is basically following the normal magnet pattern, right? Where this become or this will become the north pole, okay, and this will become the south pole, right? Because the magnetic field is entering the magnetic field is entering from this point, okay, and they're leaving at this point, right? So now this is the second case, okay, and in this case, since the magnetic field are in the same direction, and that causes the wire to be experience a force in the opposite direction, right? Because um, if you have the force, okay, so if you have the magnetic field of the same type, okay, so that causes the wire to go in the opposite direction due to the force or due to the repelling force, right? So, and this is again force on wire one, right? by wire 2 by 2, okay? And this is a force, this is on force on 2 by 1, right? And you can consider these two wire numbering, okay? So copy and paste. Okay. Now, uh if you look at this the same picture, so they look like this, okay? They look like this, right? From the top view, right? So one wire which like in where the current is coming out of the plane, okay, and the other scenario where the current is going into the plane, like the one we just discussed, okay. So in this concept, the magnetic field pattern looks like this, right? You can see over here, right? So the magnetic field pattern looks like this, okay. And in the second scenario, which was the first one, okay. So we have the two wires, okay. The two wires in their case, the currents are moving into the page, okay. And um, and the magnetic field are basically in the opposite direction, right? So wire with a current in the same direction will attract, okay, and opposite direction will repel, right? So this is what we have discussed, right? Now we sometime use this wire, okay, and we like just roll it and make a coil of a wire, okay, and that we call as the solenoid, okay. And using this pattern, right, like by using this one. So if we connect this like the two wires, or like another wire that connect the first one with the second one, so the and we have multiple loops like this. Let me show you. Like this, okay. Wait. Come on. Okay. So this is using the second scenario, okay, where you have the magnetic field. You have basically two wires, okay, one like this and the other like this, and we are connected, or we just make the coil, okay. And the magnetic field is basically in anti-clockwise or clockwise direction, depends upon the rules that we have discussed, right? But if you are converting that into the solenoid, okay, so we generally have another rule for the solenoid, okay. And the rule looks like this. The rule looks like this is do I have it? Yes, this one. Is it blurry? Yep. Okay, by the way, it look like this, okay. So if you have to work out for the direction of the current or the magnetic field in the solenoid, so you have to use you have to use this rule, okay. This is just the grip rule, okay, for the solenoid, okay. And you just need to pick the wire, okay, and curl the finger in the direction of the wire, okay, and curl the finger in the direction of the current, and wherever your thumbs open, that shows the direction of the north pole, okay. So the simple thing that you need to remember is curl the finger in the direction of current, okay. Okay, and please keep in mind conventional current is um like you have to consider the conventional current, okay. So curl the finger in the direction of uh, conventional current, which is the flow of positive charge. conventional current, okay, and the direction of thumb shows the North Pole. Okay. Okay. And the other pole would be South Pole, right? So over here, and this is basically what we call the electromagnet. Okay. So this is electromagnets, right? Now, if you place any magnetic material in it, so it become like more magnetic, right? So let me just make it smaller. Okay. So placing the magnetic material in the coil, the magnetic field will be greater, right? Or the magnetic effect or the magnetism will be stronger, right? So this is the concept, right? Um, we sometimes relate the magnetic field of the solenoid is given by mu naught n times I. Okay, this is a formula, but it's not the part of the syllabus, right? Like whenever they give you, they'll ask you, whenever they want you to use this formula, they'll mention that in the question, right? But okay, these are all of the things regarding the wire. Okay, we basically had two cases, right? In the beginning. The first one was the magnetic field due to the current carrying wire. Okay, so if you have a current in the wire, so that causes a magnetic field. Okay, and we work out every case where we have the magnetic field and its direction, right? Whether it's two wire, one wire, or like everything, right? Now the second thing is that we have to cover is the magnetic field on the current carrying wire, right? It's like there would be an external magnetic field that we create using the magnets, okay? And we will going to be placing a wire that carries current into the magnetic field, okay? And that causes a force onto that wire, okay? And we have to discuss that thing, and that will be we'll be discussing that in the next class tomorrow, inshallah. Chale, but that's it. Chale. Okay, बच्चों, टेक केयर, अल्लाह हाफिज।